Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002 and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture, we are going to talk about a very important concepts of database management system, which is query processing. So, let us look at some issues in query processing. It is not enough if the database just answers the queries, it must answer the queries in a very efficient way and in a very optimized way. So, that is why query processing is a very important part of database management systems. So, what all we have done with database management system has finally we have done all that to tackle query processing. So, here we are going to discuss the basic steps in query processing and we are going to also explain how the cost of a query is measured, and we are looking at different types of queries using different operators are handled. We are going to look at that also. So, let us first look at the basic steps in query processing. There are many steps in basic query processing. Let us look at the steps. So, this is a basic steps in a query processing system. If you look here, you give the query and then the query is parsed and translated, that is it is converted. So, suppose you say select something from something, there is a parser available, SQL parser for example, which converts it into a relational algebra expression. So, what you get as output from the parser is a relational algebra expression. This relational algebra expression is optimized. This optimization is done by using some statistics about the data, and after the optimization is done, what you do is an execution plan is decided. This is how we are going to actually answer the query. These are the databases you have to access and so on, and then comes the evaluation engine. So, here you have the data that is given to the evaluation engine, and the evaluation engine actually takes the data and gives the output of the query. So, this is the steps in a typical query processing system. Let us look at the steps again. First you have parsing and translation. So, in parsing, translate the query into its internal form, then this is translated into relational algebra. In addition to doing the actual translation, the parser also checks for the syntax and also verifies that the relationships are correct. So, it also does a little bit of verification. Then you have evaluation. The query execution engine takes the query evaluation plan, executes the plan and then returns the answer. There are some additional steps in query processing. One is optimization. For example, a relational algebra expression may have many equivalent expressions. So, there is no one way in which a relational algebra expression may be expressed. So, for example, if you have a select like this, balance is less than 2500, you take account like this. This could have been instead of having the balance here and this, you can do this way also. The order in which these two operators are performed can be different. What we are trying to tell here is there is multiple ways in which a single query can be answered, and the way in which the order in which the operators are used determine the actual cost of the query. Each relational algebra operation can be evaluated using one or more different algorithm. Correspondingly, a relational algebra expression can be evaluated, as I already told you, in many ways. So, annotated expression specifying detailed evaluation strategy is called an evaluation plan. You can use an index on balance to find accounts with balance less than 2500, or can perform complete relation scan and discard accounts with balance greater than or equal to 2500. So, what we are trying to tell here is, if you have an index on balance, then you only take out records that are balance less than 2500, that is one way. Or what you can do is take the complete relation and then discard all the accounts that balance is greater than or equal to 2500. Amongst all the equal and evaluation plans, you have to choose the plan which is having the lowest cost. So, that means obviously you have to have a method of estimating the cost. So, the cost is estimated using statistical information from the database catalog. So, what is the statistical information? The number of tuples in each relation, the size of the tuples and so on. So, now let us look at the very next important topic that we have to discuss, which is the measure of the query cost. So, cost is generally measured as total elapsed time for answering a query. So, there are many factors that contribute to this time cost. This is disk accesses, CPU or even network communication sometimes may have an effect. Typically disk access is the predominant cost. So, how many disk, the disk access is the cost that determines the total cost, and also relatively easy to estimate, and it is measured by taking into account the following: the number of seeks into the average seek cost minus the number of blocks read into average block read cost, the number of blocks written into average block read cost also. Cost to write a block is greater than cost to read. Data is read back after being written to ensure that the write was successful. Assumption is you have a single disk, but you can modify the formula for multiple disks, especially if you have what we have seen before, the RAID arrays, or you can use a single disk formula, but interrupt them as measuring resource consumption instead of time, that is also possible. For simplicity, we just use the number of block transfers from the disk and the number of seeks as the cost measure. This is a simple assumption, and that is what we do. So, here what we do is we have TT, this is a time to transfer one block, and TS is a time for one seek. So, the cost for B block transfer plus S seeks is equal to B into TT plus S into TS. So, we ignore CPU cost for simplicity. Real systems do take CPU cost also into account. We do not include cost to writing output to disk or in our cost formula. So, there are several algorithms which can reduce disk IO by using extra buffer space. Amount of real memory available to the buffer depends on other concurrent queries and OS processes, and this is known only during execution. So, what we do is we most often use the worst case estimate, so that when we actually ask the query, the minimum amount of memory needed is used, and therefore, the operation becomes better than what we have estimated. So, required data may be buffer resident already, avoiding disk IO, but hard to take into account this for cost estimation, because we do not know what is the data that is actually available in the buffer. So, let us look at query processing for different types of queries. So, let us first take selection operation. This is basically a file scan search algorithm that locate and retrieve records that fulfill a selection condition. The first algorithm is a linear search. You scan each file block and test all records to see whether they satisfy the selection record. So, the entire file block is taken and all the records are checked to see if they have satisfied the selection condition. So, the cost estimate is BR block transfers plus 1 seek. BR denotes the number of blocks containing records with relation R. If selection is on a key attribute, you can stop on finding the record. So, that time the cost becomes equal to BR divided by 2 blocks transfers plus 1 seek. Linear search can all be applied regardless of selection condition or ordering of records or the availability of indices. If you do not have indices, it is going to be much more costlier to do the operation, but here linear search does not depend on that. So, that is the easiest method, that is the linear search. The second is what is called as a binary search. So, it is applicable if the selection is an equality comparison of the attribute on which file is ordered. So, this is the best type. Assume that the blocks of a relation are stored contiguously. Cost estimate is the number of disk blocks to be scanned. It is the cost of locating the first tuple by the binary search. So, here now it is log 2 BR plus into TT into TS. If there are multiple records satisfying the condition, you have to add the transfer cost of the number of blocks containing the record that satisfy the selection condition. We see how to estimate this cost. So, index search algorithms that use an index, selection condition must be on search key. If the selection condition of some other key, then this whole thing is not useful, but if the selection condition is on the indexing, then that becomes a better one. Next is the primary index on candidate key equality. This is retrieve a single record that satisfies the corresponding equality condition. So, the cost is equal to HI plus 1 into TT plus TS. Next is the primary index on non-key equality. So, where you want to retrieve multiple records will be on consecutive blocks. So, let B be the number of blocks containing matching records, then you have HI into TT plus TS plus TT into B. So, this is the way that is calculated. So, basically we have looked at, as you can see, we have looked at, one is linear search, next is binary search, okay. Then we have looked at index, primary index on candidate key, primary index on non-key. Next we look at equality on search key of secondary index. So, retrieve a single record if the search key is a candidate key, and this will be the cost. Cost is equal to H of I plus 1 into TT plus TS. Retrieve multiple records if search key is not a candidate key. Each of the n matching records may be on a different block. So, the cost will be multiplied and can become very expensive. So, we can implement selections of the form rho A less than or equal to V of R or row A greater than VR by using a linear file scan or binary search, or by using indices in the following ways. What are the ways we use? A primary index comparison, relation is sorted on A. So, for this use index to find the first tuple and then scan relation sequentially from there. For row A is less than or equal to V, just scan relation sequentially till the first tuple becomes greater than V, then you do not have to use the index. The next method is secondary index comparison. For row A greater than or equal to V of R, use index to find the first index entry V and scan index sequentially from there to find pointers to records. If it is less than or equal to, then just scan leaf pages of the index finding pointers to records till you get the first entry which is greater than V. In either case, retrieve records that are pointed to requires an IO for each record, and a linear scan sometimes may be much more cheaper. So, up to now we have looked at simple selections. Now, let us look at complex selections where we have conjunction of row of O1 intersection row of O2 and so on. So, now let us look at complex selections where there is a conjunction of a number of selection attributes that you have. So, conjunction selection using one index. So, select a combination of theta I and algorithms A1 to A7 that results in the least cost. So, select one that gives least cost, test other conditions on tuple after fetching it from the memory buffer. So, A9 is a conjunctive selection using multiple key index, use appropriate composite multiple key index if available, or conjunction selection by intersection of identifiers. Here what we do is it requires indices with record pointers, use corresponding index for each condition and take intersection of all the obtained sets of record pointers, and then only you fetch. So, you are actually doing the intersection of the record pointers. If some conditions do not have appropriate indices, then you have to apply the test in memory. The next is this was the conjunction. Now, you have the disjunction. So, A11 disjunction selection by union of identifiers. Here applicable if all conditions have available indices, otherwise use linear scan. So, use corresponding index for each condition and take union of all the obtained sets of record pointers. Again here you are taking the record pointers and fetching the record from the main memory. Next is another type of complex selection operation, which is the negation. So, use scan on file. If very few records satisfy not theta, then an index is applicable to theta. Find satisfying condition using index and fetch from file. So, we up to now we have looked at selection operation. We may build an index on the relation, then use the index to read the relation in the sorted order, may lead to one disk block access for each tuple. For relations that fit in memory, techniques like quicksort can be used. For relations that do not fit in memory, external sort merge is a good choice. So, these are some of the choices that we have already studied in data structures, so which we are using here for accessing the records. Then you have external sort merge. So, this is an example where we are going to explain a simple actual external memory the thing has been stored. So, for that those type of operations we are looking at this. Let M denote the memory size in pages, create sorted runs, let I be 0 initially, repeatedly do the following till the end of the relation, read M blocks of relation into memory, sort time the in memory blocks, write sorted data to run Ri, increment I, and let the final value of I be N. So, after you have done this, so you have sorted and got it, then you merge the runs, it is an n way merge. We assume for now that n is less than m, use n blocks of memory to buffer the input runs and one block to buffer the output. So, you read the first block of each run into its buffer page. So, that is the external sort merge, and then you keep repeating. What do you repeat? You select the first record in sorted order among all the buffer pages, write the record to the output buffer. If the output buffer is full, write it to disk. Then you delete the record from the input buffer. You reread the record from the input buffer page. If the buffer page becomes empty, then read the next block of the run into the buffer until all input buffer pages are empty. So, this is the basic way you do the external sort. Now, we will continue with a little bit of external sort after the break. Now, let us take a short break. Welcome back after the break. Before the break, we were talking about external sort merge, and then we were talking about the repeat procedure where you have to take the first record in sorted order from all the buffer pages and then write it into an output buffer. Here we are going to look at several, if the buffer page becomes empty, what do you do? Remember what are n and m? N and m are the n way merge, and m is the number of blocks you have. So, if n is greater than or equal to m, several merge passes are required. In each pass, the continuous groups of m minus 1 runs are merged. A pass reduces the number of runs by a factor of m minus 1 and creates runs long of by the same factor. If m is 11, there are 90 runs. One pass reduces the number of runs to 9, each 10 times the size of the initial runs. So, repeated passes are performed till all runs have been merged into one. So, that is what you do. So, let us take an example here. Here you have the initial relation. Okay. Then after you have run the after you have done the run, you have here. Okay. So, you have A, D and G, A, D, G, and then here you have B, C, E, here you have D, M, R, and here you have A, D, P. So, these are the runs that you have got, 4 runs which you have done. Then you have to merge and pass 1. So, merge and pass 1, these two are merged according to the order A, B, C, D, E, G, and these two are merged A, D, B, M, P, R, and then these two are merged together to get the sorted output. So, this is the way in which external sorting is done. So, you can see that here it is all unsorted, then here within that small part you are sorting and so on. So, cost analysis of external sorting, total number of merge passes required is log m minus 1 Br by m. Block transfers for initial run creation as well as each pass in the 2 Br. For final pass we do not count write cost, ignore the final write cost for log operation. Thus, the total number of block transfers for external sorting is quite high and is of the order of this Br 2 into log m minus 1 Br by m plus 1. So, that is the cost of seeks during a run generation, one seek to read each run and one seek to write each run. So, that will take some time. During the merge phase, the buffer size BB, read write BB blocks at a time, and then you need so many seeks for each merge pass except the final one which does not require write, and so the total number of seeks becomes a significant factor as you can see by this equation. So, there are several now, so that up to now we have looked at two types of thing, one is the selection operation and the second is the merge sorting. So, here we are going to look at one other important operation of database which is the join operation. So, there are several different algorithms to implement joins, nested loop join, block nested loop join, index nested loop join, merge join and hash join, and the choice of which you will use is based on the cost estimate. Example, use the following information: number of records of customer 10,000, depositor 5,000, number of blocks of customer is 400 depositor and 100. So, to compute the theta join R, theta join theta S for each tuple TR in R and for each tuple TS in S, test pair TR TS to see if they satisfy the join condition theta. If they do, add TR TS to the result. So, this is how it is, the nested loop join is done. R is called the outer relation and S is the inner relation of the join, requires no indices and can be used with any kind of join operation. Expensive since it examines every pair of tuples in the 2 relation, that is the expensive part. In the worst case, if there is enough memory only to hold one block of each relation, the estimated cost is NR into NB plus BR, block transfers plus NR plus NR plus BR seeks. If the smaller relation fits entirely in memory, use that as the inner relation, reduces cost to BR plus BS block transfers and 2 seeks only. Assuming worst case memory availability cost with depositor as outer relation, 5000 plus into 400 plus 100, so many block transfers are required and so many seeks are required. With customer as the outer relation, the number changes, this many block transfers are required and this many seeks are required. If a smaller relation fits entirely in memory, the cost estimate will be 500 block transfers. So, block tested groups algorithm is preferable. So, we are going to look at the next one, which is the block tested nested loop join, the variant of nested loop join in which every block of inner relation is paired with every block of outer relation. So, here you can see you have a set of fors there. For each block BR of R do, for each block BS of S do, for each tuple TR in BR do, for each tuple TS in BS do, check if TR TS satisfy the join condition. If they do, add TR TS to the result, otherwise do not add. So, this is a major way in which it is done. So, worst case estimate here is again BR into BS plus BR block transfers and 2 into B seeks. Each block in the inner relation S is read once for each block in the outer relation instead of once for each tuple in the outer relation. So, the best case is as you see BR plus BS block transfers plus 2 seeks. Now, improvements to the nested block and block nested is if the block nested loop used M minus 2 disk blocks as blocking unit for outer relation where M is equal to memory size, using the remaining 2 blocks to buffer inner relation and output. This will improve the cost tremendously. So, if equijoin attributes forms a key on inner relation, stop inner relation on the first match. Okay. So, what you are doing is you are scanning the inner loop forward and backward alternatively to make use of the blocks remaining in the buffer with the least recently used LRU replacement. Use index on inner relation of if available. So, index lookups can replace file scans if join is an UKey join or natural join and index is available on the inner relations join attributes, can construct an index just to compute the J, and this becomes very useful. For each tuple TR in the counter relation R, use the index to look up tuples in S that satisfies the join condition with which is in tuple R. So, what you are trying to do is you are not trying to take two things and intersect, you are taking this, finding out what is there, and then from that you are filtering. Buffer has a space for only one page of R, and for each tuple in R we perform an index lookup on S. So, the cost of the join is again BR into TR plus TS plus NR star C, where SC is the cost of traversing the index and fetching all matching S tuples from one tuple of R, and C can be estimated as the cost of a single selection on S using the join operation. So, this is basically what we are trying to say. If the indices are available on join attributes of both R and S, use the relation with fewer tuples as the outer relation. Now, why are we doing this fewer in the outer and more in the inner? Because already when you are doing the outer, certain things get filtered. So, for example, compute depositor join customer with depositor as the outer relation. Let the customer have a primary B plus tree index on the join attribute customer name, which contains say 20 entries in each index node. Since customer has 10,000 tuples, the height of the tree is 4 and one more access is needed to find the actual data. Depositor has 5,000 blocks. Cost of the block nested join is equal to 400 into 100 plus 100, that is equal to 40,100 block transfers plus 2 into 100, that is 206. So, this is assuming the worst case memory may be significantly less with more memory. So, the cost of the indexed loops join is equal to 100 plus 5000 into 5, this is approximately block transfers and 6. CPU cost likely to be less than for block nested block join. This is in the loop join, nested loop join. Next you have the final or another important join, which is the merge join. Sort both relations on the join attribute if not already sorted, and then you do the merging. The merge of the sorted relation is to join them. Join step is similar to the merge of the sort merge algorithm. The main difference is in handling the duplicate values in join attribute. Every pair with same value in join attribute must be matched. Detailed algorithm is available in books that you can read up. We are not looking at that. So, let us look at merge. So, here you have the merge. So, you can sort this accordingly. Now, can be used only for equijoins and natural joins. Each block needs to be read only once, assuming all tuples for any given value of the join attributes fit in memory. Thus, the cost of the merge join is BR plus BS block transfers plus BR divided by BP and this many 6 plus cost of sorting if relations are unsorted already. So, then you have something called a hybrid merge join. Now, here if one relation is sorted and the other has a secondary B plus tree index on the join attribute, merge the sorted relations with the merged entries of the B plus tree, then sort the result on the addresses of the sorted relocation tuples, and then what you do, you scan the unsorted relation in physical address order and merge with the previous result to replace addresses with the actual tuple values, but here sequential scan is found to be more effective than random scan. This hash join, which you have seen in the last lecture, is again used here. Application for equijoins and natural joins. A hash function h is used to partition the tuples of both the relation, such that one part resides in memory and the other does not reside in memory. So, h maps just like before when hash join we used, it maps the join attribute values to 0, 1 to n, where join attribute denotes the common attributes of R and is used in the natural join. So, suppose you have R0 equal to R1, R2 to Rn, denote parameters of R tuples. Each tuple belongs to R is put on partition Rj, where I is equal to HR join attributes. R0 to R1 denotes the partitions of S tuples. Each tuple Ts belongs to S is put in the partition Si, where I is equal to this value. So, basically we are putting it in two partitions. So, suppose this is the data, these are the partitions of R and these are the partitions of S, which is again later connected to a database. So, R tuples in Ri need only to be compared with the S tuples in Si, need not be compared with S tuples in any other partition. So, if an R tuple is an S tuple that satisfies the join condition, will have the same value for the join attributes. If that value is hashed to some value I, R tuples has to be in R and the S tuple has to be in Si. So, the hash join and S is computed as follows. You partition the relation using function h. When partitioning a relation, one block of memory is reserved as output buffer for each partition and one block for input. If the extra memory is available, allocate BB blocks as buffer for input and each output. Partitions are similarly. For each partition, what you do? You load S into memory and build an in-memory hash index on it using join attributes. This hash tape indexer uses a different hash function than the earlier one. So, this is a different hash function. Read the tuples in Ri from the disk one by one. For each tuple TR, probe the in-memory hash index to find all the matching tuples. For each matching tuple, output the concatenation of the attributes of that particular variable. Variable value n in the hash function h is chosen such that each S j should fit in memory. Typically, n is chosen to be Bs divided by m star f, where f is the number of the fudge factor, so called fudge factor, typically around 1.2. The probe relation partitions Si need not actually fit into main memory, it can be in secondary memory and then also you can do. Recursive partitioning required if number of partition n is greater than the number of pages m of the memory, then instead of partitioning n ways, use m minus 1 partitions for S and further partition the m minus 1 partition using a different hash function. So, you have to use the same partitioning method that you have used for R. So, next comes the question of handling overflows. Here also overflows can occur. So, partition is said to be skewed if some partitions have a significantly more tuples than others. So, hash table overflow occurs in partitioning Si if Si does not fit in memory. Reasons could be many tuples in S with same value for the join attributes or bad hash function, both phases. So, overflows resolution can be done in build phase while and the partition S is further partitioned using another different hash function and the partition Ri must be similarly partitioned. Overflow avoidance performs partitioning carefully to avoid overflows during build phase. Partition build relation into many partitions and combine them. Both approaches fail with large numbers of duplicates. Fallback option, we use block transfer instead of nested loops join on the overflowed partitions. So, hybrid hash modulus as given, useful when memory size is relatively large and the build input is bigger than the ontology. Main features of the hybrid cache joiner: keep the first partition of the built relation in memory and then you have to do duplicate elimination. So, this duplicate elimination you can do in different ways, it can be done by hashing or sorting, and perform projection on each tuple and followed by the duplicate elimination. So, another operation that you do on database is aggregation. This can be implemented in a manner similar to duplicate elimination. So, here we have discussed the basic steps in query processing. We have briefly explained how query cost is measured for different types of queries like selection, complex selection, and then we have discussed in detail how the different types of queries using different operators have handled, that has been discussed here. So, explanation in detail of the basic steps of query processing and then discuss in detail how the cost of query is represented using any of the all the methods. You must give the cost for all the methods. And explain in detail how query processing in the case of string processes is done only for that, and then discuss in detail the handling of queries with different types of joins, nested join, equi join and so on. Thank you.